Anna, and welcome to our day's lesson. That is majorly going to be on still on properties of matter, but specifically we're going to look at this issue of expansion and contraction. Expansion and contraction simply mean becoming bigger and reducing something in size. For example, we talked about in some time back in a lesson of science like today. We looked in details the issue of liquid thermometer and air thermometer. And we say that both of them operate on the principle that liquids expand when heated, and even air also expands when heated. So both of them, liquid thermometer, we use a liquid, and then in air thermometer we have the two of them. We have the two of them. One liquid is placed down here, and then when the air up here expands, the liquid there will push down. That's why this one we normally name from up. Number 1, 2 coming downwards. Contrary to the liquid thermometer, where you are putting this, there was a liquid here, and it could number starting from downwards going upwards. So this liquid, when it receives heat, it was expanding. You could see the liquid expanding, hence you could read going upwards. But this one, because the air up here was expanding, when we have a hot environment, it will automatically expand, and we'll see the level of water here being pushed, so we could read going downwards. And again, what you know is that when the temperature is low, meaning when this is a cold environment, we'll experience this liquid will contract. And when it contracts, we'll see the decline. You can see the decline of temperature. And then this one, when the temperature reduces, automatically this thing will contract. The liquid here will contract, hence will read low temperature there. So we also mentioned that temperature is read in degrees Celsius. It's read in degrees Celsius, really like that. Degrees Celsius is the unit of measuring temperature. So as we go to this expansion and contraction, we need to know that matter expands when heated. Matter expands when heated. All of them, we normally have the 3 states of matter. All liquids, solids, and gases, all of them expand when heated. And then matter again contracts when cooled. We use that term. When cooled, the meaning when you expose a low temperature, like you put something in a fridge, that is a low temperature. When the temperature is low, it cools. And when you expose matter to a strong environment, to heat, for example, increase the temperature, matter will expand. So in which we also have this. To expand means to become bigger or occupy more space than before. Yes, to become bigger. Like we look at a very good example. When we heat, let's take an example of this. A metallic ball, when heated, let's take this metallic ball. These are ring. So when we heat a metallic ball, that can simply pass here. One that can pass here loosely, it can pass inside this place in a loose way, this ball of ours. It can go through this place in a loose way, meaning you don't need to force it to go. Then when you heat it, thoroughly with fire or on heat, it may not pass through there again, because it shall have increased in size, meaning it has expanded. Due to heat, it has expanded, hence it may not go in that. But when you cool it, after cooling it, it can easily pass because it has contracted again. Normally you normally have the kiwi lids, a kiwi container, the shoe polish container. Normally in that, let me draw just a simple one. It may look like that. This is the one carrying the shoe polish, and then this is the lid. So you may realize that when you remove this lid away from it, then you heat the lid. on heat. After heating the lid, it may, if you take it there, it may not fix it, it may loosely fix that thing because it shall have increased in size. So it may not really fix in that particular place. But when you cool it later, it may now fix tightly onto the lid. So that's just an example, Anna. To contract means to become smaller and to occupy less space than before. So let's look at expansion and contraction on solids. Where do we experience a number of expansion and contraction on solids? So number one, on solids we are going to see the electric cables. The electric cables is going to be our number one, the application. The electric cables. So when we look at this, we have however seen the electric cables at home where we stay. We have ever seen them, so let's draw a sample here. Help us to see. They'll always behave on a manner that the way I've drawn it. And then I'll draw two of them. That's the first one. Then another one may behave like this. Another one may behave in this manner. So you can see them, there's a difference between our first cable and our second one, the electric cables. So these are the poles. Normally you have the poles, electric poles, and the electric cables. So as you can see them, these ones are loosely, they are in that form they are. Very early in the morning and late in the evening when there is less heat. Normally know that there's a lot of heat during the day, like now. But later, early in the morning and late in the evening, we have less heat. Hence, the environment is very cool. So very early in the morning, this one is very early in the morning, and late in the evening. We'll expect our cables to look like that. They are very flat. There is no warpings like you can see here. We have warpings. They're in a wave shape. So we can realize, like we are learning today, that very early in the morning and late in the evening, when it's cold, the cables become tight, as shown in that diagram. They become tight. They become tight the way I've drawn them there. They become very tight. You see them, that there is no any warpings as I've drawn them in that picture. And then in this particular case here, so what makes them to be tight, Lana? I've just shown that we have the environment is cool. It is cold. So when it's cold, we expect the cables to be in that manner. When it's cold, they contract. And when they contract, they behave like that. They behave in that manner. When they contract, they behave in that manner. But later on, when during the day, now don't say the meaning of that. This is because the cold weather makes the cables to contract and become firmly stretched. When they contract, they become firmly straight, and that is what makes them to be tight. And then when it's hot, especially in the afternoons, the cables hang loosely. This is when it is hot, especially in the afternoons. They hang loosely, the way I've drawn it there. And ask yourself, why do they hang loosely? They hang loosely in that manner. They hang loosely. They hang loosely as shown in the diagram, the way I've drawn it there. Why? Because the cables become loose because the weather makes them to expand and extend. The weather makes them to expand. So these ones expand. When they expand, they behave in that shape. After look at that now, go to the number 2. That is going to be, number 2 is going to be the railway line. The railway line. So in the railway line, I hope you have ever seen a railway line anywhere. Mostly in town there we have a railway. In most cases you see them fixed in this manner. Between one rail and another rail, there's a gap normally left there. Between one rail and the other, there's a gap normally left. And these gaps, again, they are tied using something to make them be fixed together. But there's a space left, a small space left there, between one rail to the other rail. So that space, there's a rail bus and then there's a gap. There's a gap left here. These are rail bus. So that space learn is only going to learn the use of that little space. Railway lines are made on metals, which is a good conductor of heat. So they are hot, they are not continuous but have a spacing between the rail bars. Why? This space allows for expansion during hot weather. So the work of this space here allows for expansion and contraction during hot weather. During a hot weather they'll expand. And when they expand, the gap will be reduced. This gap will be reduced, meaning this one shall become big, this one will also become big, then at least they have a space to expand. When you don't leave that space, what will happen? The railway will expand and then they will end up breaking. Yeah, so to make them be firm enough, we leave a small space there to facilitate expansion and contraction. So much for that. Then we go to our next number. That is the ball and ring experiment. The ball and ring experiment. The ball and ring experiment. And this one here is also very nice and very I did it before. The ball and ring experiment. I told you that we can easily take this one is a ring. This one is our ring. And then we put a ball. This is a string that holds the ball that has just passed through that place there. This is our ball. And our ball is held using a string that has gone through this ring here. This is a string that holds our ball. So it can pass through the ring easily. But when we hit it, when we put a source of heat, to hit this thing here, under here, when there is a source of heat down here, we hit it, it may no longer pass through the place again because it shall have expanded. So when we hit it, it may expand and fail to pass through the ring again. So expansion and contraction of gases. That's what we are now going to. On gases, you'll realize that if we put a bottle, let's just talk of a bottle, a metallic bottle or a glass bottle, and we tie a balloon here, a balloon without air inside. If we put a balloon there, you'll realize that air will deflate automatically. There's no air there. But when you try to heat it, when you put heat under this place, when you put heat there, Lana, the heat there is going to make the air inside this bottle to expand. And once the air expands, Lana, you'll see the balloon automatically. The balloon will inflate automatically. Meaning the air here shall expand to fill the space that is there in the balloon. So by that we shall say that the air, after heating the bottle, for some time, air in the bottle expands and rises up the bottle into the balloon, therefore inflating it, meaning air expands when heated. Air expands when heated. It expands, the way I've shown it there. Another one is a case where we have a bottle. We have a bottle. This is water. And then we have a bottle coming from up there. We have water in this particular basin of water. This is about, then we have a straw. There's a straw there. And then we have a bottle. And then we have a heat. So we are heating this particular. There's a source of heat that is heating this particular. So we have heat here. So when we heat that particular this container, when we heat it, maybe you can hold this thing. Somebody can hold it using something. When it's held and we heat this particular bottle, the air inside here shall expand. And when they expand, we shall see bubbles coming out from that place. Why do we see the bubbles, Lana? The bubble is a sign of expansion. The air inside the bottle expands into the water, into the bottle, into the water. And into the water you can easily see the bubbles coming out. And again, after some time when you remove the source of heat, we shall see no bubbles. Why? Because the air there shall contract. And when it contracts, it can't come out in form of bubbles again. So expansion and contraction again in liquids. In liquids, we had learned that in as far as the liquid thermometer is concerned, we said very well that when we heat that liquid, when heat hits it, it expands and we can therefore read. And there we also have just a small experiment. We have shown expansion in solids, that is the cables and the ring and the ball. You have seen in gases how if we heat the gas, air expands. If we heat a container, the air expands. And now we are going to water, where if we heat the water inside here, if we heat the water, in this case we are going to put a straw, and this water is colored. We will enable us to see clearly. So this water shall rise when we put heat. When we put heat down here, this water shall rise to a level depending on the heat, the quality of the heat. The water will rise. Why is it rising? Because it expands. This thing expands. Because before you reduce the heat, there was an expansion. But as soon as we reduce the heat, it expands. And when you remove the heat completely, it starts coming down. There's contraction of the liquid again. So gases expand more than liquids, and liquids expand more than solids. You need to know that quantity. Which one expands most? Gases has the greatest expansion. So gases expand expand more than the liquids. And again, liquids themselves, liquids expand more than the gases. No, more than the solids. So the vice versa, gases expand more than liquids, but liquids expand more than solids, meaning solids expand the least, followed by liquids that follow the liquid, the solids, and then gases expand more than all of them. Measurement of temperature is in degrees Celsius, and the spelling of degrees Celsius is this one. At times, the short form we said that temperature, in short, at times we call it temp, right? In short, is measured in degrees Celsius. That is in short, but in full, that degrees Celsius is written in form of degrees. Degrees Celsius. Celsius. Degrees Celsius. That is the spelling. So temperature is the hotness or coldness of a substance or a place. We know that. Like the temperature today is hot, maybe. It's the degree of hotness or coldness of a place or a substance. And when it's cold, the temperature is low. When it's hot, the temperature is very high. Temperature is also measured using a thermometer. An instrument called a thermometer. We have discussed that. Then the temperature, the thermometer used by a doctor to measure our temperature. Nowadays we have the thermometer gun. But before thermometer gun was there, we had something called a 60 thermometer. Something called a clinical thermometer. Clinical thermometer. Used by what? A doctor. The so-called thermometer gun is still an example of a clinical thermometer. Still used in the hospital. Clinical thermometer used by the doctor. It also uses the same principle of expansion and contraction. Let me just do a simple one for us to see. Then it has a small tube inside here. Looks like that. Then we have the units of measurements, named 1 to the in level, 1, 2, 3, 4, 7 level. We set numbering from this side. So 1, 2, 3, 4, as we can make the other side. So we have the mercury. Here it uses something called a mercury. Mercury is just a liquid that is colored. It can be easily seen. We use a mercury because it can easily expand, and again, it is visible. We can easily see the measurement well. You can't use water because water is clear. And again, we have a fine tube inside here. We have a fine tube. And then we have a constriction. Constriction is this part. Constriction. And then we have the thermometer scale. We have a scale here for measuring. So when the doctor wants to measure your temperature, he'll put this thing under your armpit or in a part of the body, just in a part of the body. And then your temperature, depending on the way it is, shall make the mercury to expand to a given level. And when the mercury expands, the doctor will be able to read at which level it has expanded to read your temperature. When your temperature is so high, meaning this thing shall rise to a great level. And when your temperature is very low, meaning it will expand just a little. will not expand much. When it expands much, meaning your temperature is so high, as qualify to be quarantined because of COVID-19. That's a joke. So the scale of the clinical thermometer runs from 35 degrees Celsius to 42. It runs from 35 degrees Celsius to 42 degrees Celsius. Meaning don't expect a human body to go below 35 degrees Celsius. We expect the standard temperature of somebody should be around this. Then if it goes to 42, meaning it's so high, then you are sick. Then because the normal body temperature of a human being is 37. We need to know that. The normal body temperature is 37 degrees Celsius. The normal temperature of a human body should be around 35, meaning 35, 36, 37. 37 is the normal body temperature of a human being. So the thermometer has a constriction, and the work of the constriction there, I've drawn it here, this one here. The constriction learner, that is a small curve that prevents the mercury from running back into the bulb after moving it from the body. So when you just remove it from the body, learner, this constriction will help the doctor to still read without it going back immediately. Shall go later, slowly by slowly, but can't go abruptly after removing from the body. When I'm measuring, when the doctor will remove it from that base, I let up on the poly, I sound it. So when we don't have the constriction, the mercury will go immediately back and the doctor will not be able to read. But because of that, the doctor can be able to read very well, and the constriction will help the temperature not to drop abruptly. Then the mercury is the preferred liquid used thermometer because it can be seen clearly through the glass. Then temperature is measured in degrees Celsius, and the scale on an ordinary thermometer is marked from 0 to 100. An ordinary thermometer has no constriction. An ordinary one is just a normal one without, away from the one used by the doctor. The one used by the doctor is a clinical thermometer that has a constriction. But an ordinary one, the temperature runs from, we read from 0 to 100 degrees Celsius. But in the doctor's one, it reads from 35 to 42. So we have two types of thermometers, the ordinary one and the clinical. Clinical one runs from 35 to 42. But the ordinary one runs from 0 to 100 degrees Celsius. And remember, the ordinary one has no constriction because there is no decline. There's nothing that we are going to use the constriction for. As compared to this one, we use a constriction to make the mercury not run very fast for us not to read well. So we have also this. The temperature at which water freezes is 0 Celsius. And right here, water freezes at 0 degrees Celsius, and then water boils. Boiling point. Water boils at 100 degrees Celsius. So you see water boiling, meaning it is 100 degrees Celsius. And you see water freezes, like water put in the fridge, that thing is, measure it, it's going to be 0 degrees Celsius. So now how does it stop there? So that lesson is over. We are done with this book of class 5. We're now looking forward for strict revision, much revision, for us to gather whatever we didn't get. Hence, you're going to be more well equipped with the knowledge as far as science is concerned. Until next time, let us stop there. I wish you well. I'm going to be giving you work every day, every time of science, for us to continue being acquainted with knowledge. I wish you well.